Well, hi everyone. Just make sure this mic is on here and working. Can you hear me okay? Okay. So today what we're going to do is we're going to cover probability. I just want to remind you of what's due this week. Here we are. So this homework covers last week's lectures. And except for, I think homework 4 starts the probability. It covers some of chapter 6. So also here, I strongly recommend you watch these pre-lectures. And then our first assignments, assignment 1 is just making sure you can sign up for Get On R, and the assignment 2 actually has you do simple calculations. They're both on Lon Kappa. So any questions on that before we begin? All right. So let's go to the document camera then. Okay, so probability. What I'm going to be doing in probability is really simple stuff, and most of you probably have already seen this, and a lot of it is intuition. So the reason that we're going to cover probability is because we're moving on to inferential statistics, and all the methods that we're going to be using in inferential statistics rely on probability models. So it's a good point right now to just review, or for those of you maybe learn for the first time, some simple probability rules, the multiplication rule and the addition rule, and a little bit of conditional probability, Bayes' rule, and that's what we're going to be doing today. Okay, so some of it is just super easy. You don't have to get it don't have to get complicated. What is the definition of probability? Well, the simplest one is to think of it as the second one. The probability of an outcome is the number of that outcome over the total number of possibilities. And this total number of possibilities right here is referred to as the sample space. So, move this up a little bit. So the sample space, what's the sample space for rolling a fair die? A fair die like this. What's the sample space? Well, there's 6 possibilities. You could get a 1, a 2, a 3, a 4, a 5, or a 6. Okay, so what's the probability of rolling a 5? Well, out of the 6 possibilities, out of the 6, the probability of that outcome is the number of that outcome is 1 out of 6. Okay? So what's the probability of drawing a queen of spades from a deck of 52 cards? Okay, so the queen of spades, well, just in case you haven't seen cards, there's 52 of these, and they have 4 suits. I'll write it down here. 52 cards total. And there's 4 suits. The suits are hearts, diamonds. It's hard to draw the others. I'll show them to you. Clubs and spades. So they look like this. That's a spade and that's a club. And then the numbers for in each suit, 4 suits, but in each suit there's 13 cards. There's the numbers 2 to 10, and then there's these picture cards, like a jack looks like that, and there's a queen and a king, and an ace. So there's 4 suits, and there's 13 cards in each. 13 times 4 is 52. So that's it. 2 through 10, and then there's a jack, a queen, a king, and an ace. So that's the cards. Now, what's the probability of drawing the queen of spades? So there's, from a deck of 52. So 52 possibilities. There's only 1 queen of spades. Here's a queen of diamonds. The queen of spades looks the same, but it has spades. So that's just 1 out of 52. Okay? That's the probability of the queen of spades. What's the probability of drawing a queen? Well, still there's 52 cards, and there's 4 queens. So that's 1 out of 13 and 4 out of 52. How about an even number on a fair die? Well, there's 6 possibilities, and there's 2, 4, 6. 3 of them are even, and 3 of them are odd. So you can, of course, you can reduce those fractions. So now the probabilities, range from 0 to 1, or 0% to 100%, even though people say, 100, give it 110% or something. If it's sure to happen, if something's sure to happen, we call it 100% or 1. And if it's sure not to happen, it's 0%. So there's no negative probabilities, and there are no probabilities greater than 1. Now, this is, so for events that either happen or they don't, the probability of A, the complement of the event A, is the probability that it didn't happen. That's what it says. So it's the complement of an event A is the set of all outcomes in the sample space not included. So basically, all it is the probability of A equals what? The probability that A happens and then the probability of not A, which we call A complement, of A not happening, either happens or it doesn't, is equal to the probability that A doesn't happen. Pretty simple. So obviously, the two have to add up to what? The probability that it happens plus the probability that it doesn't happen has to add up to 1 or 100%, depending if you're talking percents or between 0 and 1. Okay? So why this is useful often, because sometimes it's easier to figure out the probability that something didn't happen rather than the probability that it did happen. So often you should think about this when you have trouble figuring out the probability of A. Sometimes it's easier to say, okay, I know that, 1 minus the probability of A complement. So these are, what's the probability of not rolling a 5 with a fair die? Well, that's pretty easy, not rolling a fair die. Well, that's probably, we could say, okay, the probability of not rolling a 5, you could figure out that directly. Out of the 6, there's 5 that aren't 5s, but we could also say 1 minus 1/6, or this one's very easy to figure out directly, or you could just figure it out directly as 5/6. I don't need to tell you that. So the probability of not drawing a queen, okay, the probability of not drawing a queen, the probability of a queen is 4 out of 52. So you could just say 1 minus 4 out of 52. In these cases, obviously, they're very easy to figure out the probability of a not queen directly and the probability of a not rolling a 5. But it's useful in many other examples that we're going to see. So this rule is very useful. This right here, it's going to come up a lot when it's useful when the probability of A is hard to figure out, and the probability of not A is easy. Okay, so what happens if I turn it that way? Just having a hard time writing like this. Okay, now let's move on. And we're going to talk about independence, which is a very important idea in statistics. Okay, so two events are independent. What? If the probability of the second event does not depend, is completely independent, does not depend on what happened on the first event. For example, independence would be, let's say I rolled a 3 on the first roll. Does that change the probability of me rolling a 3 on the second roll? No, they're completely independent events. Oh, I did. But that's not because I rolled the 3 on the first. Unless it was a loaded die. Let's see what else I get. 5. Okay, so the die has no memory of what happened. It's going to be the same each time. So the events are independent. Same with flipping a coin, etc. Events would be dependent when the probability changed. Like if you had a die that had a memory and said, oh, I gave you a 3, maybe I won't give you a 3 the next time, just to change things up, if it had some memory in it. Or like cards. So let's think about cards. Let's look at these examples. Draw 2 cards with replacement. Is getting a heart on the second card independent of getting a card on the first? And the key word right here is with replacement. With replacement. So the probability of getting a heart on the second card is that doesn't matter what I get on the first card because I'm putting it back. It's just like the die. So the probability of getting a heart on the second card is going to be what? No matter what I got on the first card, how many hearts are there? There's 13 hearts in here, right? It's 1 out of 4. It's 13 out of 52. So the probability of a heart on second card doesn't change depending on what's on the first card. Okay? They're independent. Why are they independent? Because the probability is the same regardless of what the first card is. The two events of what? What you get on the first and what you get. This doesn't depend, so it's independent because the probability remains the same no matter what you get on the first. Okay, but if you draw without replacement, okay, is getting a heart on the second card independent of getting a heart on the first card? Yes, because what? If I get a heart on the first card, say I got this heart, and now the key thing to think about is that it's without replacement. So I'm not putting that card back. So the probability of getting a heart on the second card is going to be what? How many cards are left? How many hearts are left? The probability of a heart on the second card, given that I got a heart on the first, is what? Well, there's 51 cards left, and how many hearts are left? 12. There were 13 to begin with, and now there's 12. So that changes. That's different. That's probably on the second card is 12 after if first is a heart. But the probability on the second card is equal to what? Let's say it wasn't a heart. Let's say it was something else. It's a diamond. Now it's going to be still 51 cards, but how many hearts are left? All the hearts are left. So there's 13 hearts left. So if first is not a heart. So without replacement, those probabilities are dependent. okay? All I'm saying is this. When you draw with replacement, the deck changes. So when you draw with replacement, the deck doesn't change. With replacement, the deck doesn't change. So the probabilities are independent. They don't affect each other. Without replacement, the deck changes. So you have to think. This is why, if you're playing cards in Vegas, you actually, if you think about what's already been taken out of the deck, because if they don't replace it, if you're really good at this, you can actually win. Whereas all the other games are independent events, like roulette is an independent event each time they spin the wheel. But if they're dealing out cards and you keep track, the probabilities change, so you get an advantage. And you can really, super smart people can keep track of those probabilities, can win at blackjack. Okay, so now the multiplication rule. All right, so what happens when, this is the probability that two things both happen. The probability that both A happens and B happens, okay? So, for example, the probability of getting, flipping a coin and getting first ahead, and then flipping, that would be one event, ahead on the first flip, and the second event would be ahead on the second flip, okay? So that would be two heads. Wouldn't you multiply those two together? You'd say half the time you get ahead, and half of those times you get another head, so your chance would be 1 out of 4 of getting two heads. Those are completely independent events. So the idea is that if you want the probability of two things happening, the probabilities get smaller, right? You multiply those probabilities. So the probability of the probability of A and B, those two things together, the probability of A and B, it's multiplication rule. It looks like adding here. Don't get confused. No, the probability that A happens and that B happens is smaller. They both have to happen. So it's the probability of A times the probability of B, okay? I'm going to leave this a little bit blank there, but we have to think about, did B change or not? Like the probability of getting a queen. If we're in this case without replacement, we have to think about the probability of getting a queen on the first, and then getting a heart on the first, a heart on the first, and then a heart on the second. We have to think about if it did it change? Whereas in this case, we didn't. We could just say, oh, probability of getting two hearts is just 13 out of 52 times 13 out of 52. But if we're in the case where they're dependent, right here, without replacement, this is dependent, and this is independent. If we're in the dependent case, we have to think, did we get that heart on the first? All right, so the general rule right here, when we're multiplying probabilities, is you say probability of A times the probability of B if they're independent, sure, because it doesn't matter. But you have to always think of the probability of B given that A happened, okay? So that's what this is saying. The probability that two events will both happen equals the probability the first will happen, multiplied by the probability the second will happen, given. That line right there means given. Okay? Now, when independent, if independent, this is a special case. When they're independent, it's a special case of this because the probability of B given A doesn't matter. It's just the same as the probability of B. So if the two events are independent, you can just think the probability of A plus B equals the probability of B times the probability of A. So this is the general rule, and this is a specific example of it. Because the probability of B given A, I shouldn't have switched that. I should have just said probability of A times the probability of B, sorry. Because these two things are the same. So that's the idea. All right, so let's think about this. Now, a box has 6 tickets. Let's see, 6 tickets. Let's draw them down here. And let's make a box with 6 tickets. And what does it say? 3 reds, 2 blues, and 1 yellow. So 3 reds, 2 blues, and 1 yellow. That's what the box looks like. Those are tickets. So what's the probability of drawing 2 blues from the box now with replacement? It's going to be independent, right? Independent. So the probability of getting a blue, 2 blues, and another blue, this is going to be really easy, is just the probability of blue times blue. So there's 6 tickets. 2 of them are blue. So we take out a blue one, but then we put it back in. The probabilities remain the same. So it's times 2 out of 6. Okay, which is 1 out of 9. But what if we do the same thing without replacement? Do the same exact thing without replacement. Then we have to think, okay, the probability of blue and blue. Well, the first event, remains the same, blue. But now we don't put it back. So now it's going to change. What's the probability of getting a blue now if we don't put that back? It's not 2 out of 6, because these events are dependent, getting a blue in the first and getting a blue in the second. So now there's only 5 tickets left, and there's only 1 blue left. So this one changes depending on what happened in the first one. So these are dependent events. The first and the second draw from there. Any questions on that so far? Okay. Now, back to this idea. The probability of an event occurring and not occurring equals 1. Okay, so here's these 2 useful cases that I said would occur, but I don't think I said page 30. Did I say when it would be useful? So this is an example of when it would be very useful. All right, to figure out the probability of something not happening. Okay, the probability of at least 1 is hard to figure out, because at least 1, depending on how many things you're talking about, is 0. I mean, it's everything but 0. It's 1, 2, 3, 4, 5, 6, everything but none. So those 2 things are complements, and it's easier to figure out the probability of none. Same with this example. So let's look at this. When drawing 2 tickets with replacement, okay, it's the same example. Here's your box. There's 3 reds, 2 blues, and a yellow. So it says, first of all, with replacement, so they're independent, all right? What's the probability of getting at least 1 blue? So at least 1 blue is going to be, you have to think about it as, okay, so at least 1. What are the options here? So you think the probability of at least 1 blue, let's just say it's the probability of at least 1 blue is equal to 1 minus no blues. That's easier to figure out than on 2 tickets. With 2 tickets, let's say we have 2 tickets. What are our options? Our options, we could get 0 blues, we could get 1 blue, and we can get 2 blues. Right? We can that. Now, at least 1 is this. This is at least 1. And this is none. And together they add up to 100% or 1. Now, why is this one hard to figure out? Because one blue, you'd have to think of getting a blue on the first and a not blue. Then you'd have to think of a not blue and a blue. And then you'd have to think of 2 blues. It's not that hard. There's 3 possibilities you could do that. But it's much easier to see the chance of no blues, because you only have one thing to figure out, okay? So that's why it's easier, which is equal to 1 minus, what's the chance of no blues on the first? There's 4 other tickets, so it's 4 out of 6, and it doesn't change, times 4 out of 6. So that is 36 minus 16, 20 out of 36. Okay. So you could do it directly if you want, this way, and you could try that. You want to do this, you could try that right. You know, that's not very hard. You can see it's the same. This would be, I don't want, do you want me, you could do it on your own. You want me to do it, I'll do it, but you could probably just do it in your head. Okay. What's the probability of drawing 2 tickets without replacement and getting at least, now we're without replacement. Okay, without replacement. And so what are we going to do? It's going to be the same thing, but this was independent, and now this is going to be dependent. So we'll say the probability of at least 1 blue is going to be equal, how is it going to change? The probability of at least 1 blue, it's still going to be 1 minus the probability of no blues, but this second one's going to change, right? The first no blue is 4 out of 6, but now suppose it doesn't matter what we chose, we're not going to put it back. We just know, given that we got one that was not a blue, how many tickets are left? 5, and how many are not blues? 3. So now that's your answer, and so it changes. Okay? And the idea is that this is easy to figure out right here. This one's easy, and this right here is easy to figure out, and this is hard. So that's why when we see at least 1, we use this rule. Okay? And especially as you get more, let's say it was, we drew 3 tickets or 4 tickets out of the box, then we could get at least, then it would be very hard to figure out. Okay, so now let's look at the second rule, the probability of all plus the probability of not all. So we can look at that rule, and it's the same idea, that the probability of all, let's think about this, the probability of all would be what? 3 tickets now. So what are our choices? We could either, in getting all reds, okay, so what could we get? We could get 0 reds, we could get 1 red, we could get 2 reds, and we can get 3 reds. Those are our possibilities, right? And now, all reds is this, and not all reds is that. So all reds is easy. We can do that one easily. Getting all reds is just this. So this is the problem. And is it with replacement? So that's pretty easy. So we can figure this one out directly, right? The probability of all reds. There's just one way it can happen. It's getting a red on the first, which is 3 out of 6, times a red on the second, times a red on the third. So it's just that. But now what about not all? Not all reds. So this is easy. This is all, and that's easy. But this right here is hard. And they add up to 1. Okay? So now when it asks for not getting all reds, and it's with replacement, what do we want to do? It's also with replace. with replacement. It's not all. So instead of figuring out that directly, it would be really hard this time. We'd have to figure out, you could get red on the first, but not on the next two, on the second one, but not on the, so this is going to take you a long time. This is hard, but this one's very easy. Okay? So it's just what? This one's all reds. And this one is hard. Okay, so you'd say the probability of not all reds is equal to 1 minus the probability of all. So that's equal to 1. Because you have to figure out all these possibilities. Any questions on that? All right, so let's move on. Oh, you had a question, sorry.
Why is it 6 instead of 3 with the graph? Like, why do you have the exponent of 6? Is that how I'm saying?
1 minus 3/6 to the 6th?
Yes.
Oh, because why is it not the whole equation? Because what we're doing here is this is 1 minus, and what's the probability of all reds? Right there. Does that make sense now?
Yeah.
Okay. Any other questions? Okay. His question was, why wasn't the parentheses around the 1, 2? Okay, now what's the probability of rolling a die twice, a fair die, and getting a 5 and then a 6? So we want the probability of a 5 and a 6. So this one's pretty easy. What is it? 1/6. Multiply, you want both to happen, and they're independent, times 1/6. So I think these are pretty easy. You can probably do all these yourself. Do you want me to do it with you? I could. What's the probability of drawing 2 cards from a deck with replacement? Okay, and first a heart. A heart is what? How many hearts are there? 13 out of 52 times 13 out of 52. It's with replacement. Now if you're going to do it without replacement, now you have to think about how this second one changes, and it would be 13 out of 52 times out of 51, because we're not putting that card back. So now we only have 51 cards left. How many of them are clubs? We didn't draw a club, so there's still 13. Okay? Any questions on that? So let's move on. Oh, was there a question? All right, so these are just moving along, doing the same thing. Maybe you should, let me see if there's any that you want me to, that you might want me to look to. Let me think. Here, let's do the first one. And actually, these are all just the same. Do you want me to, how about you do these on your own, and I'll post the answers? It would be good practice, because these are just what we've covered is better. So this is complete on your own. Answers I'll post on the calendar. Under the video. I'll just post a PDF there. I think it's easier if you just do, these are pretty easy to do on your own. If we had time, you'd do them right now, but I don't think we have time, so. If you're watching this online, you should do them now. Okay, so now we're going to move on to conditional probability. We've talked about that before, the probability of A given that B has happened. Okay, so let's look at this. All right, what are we talking about here? The conditional blah, 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 I'm sorry. Okay, this probability is written as the probability of B given A happened, or given A. All right. Okay, so this says the probability of B given A happened is the probability of A and B divided by the probability of A. So the picture for this would be what? Okay, so let's say you have event A and you have event B. And this is saying, what's the probability of B, this is the whole probability of B, given that A has already happened. So that would be this intersection right here. So that's what this part is. So your probability of B given A happened would be just this little part right here. This right here, this intersection, is the probability. It's the same as the A intersection B, and it's the probability of A and B. And so you can intuitively see why that's true. Given that you're here, that A has already occurred, your probability that B happens is just that little slice. But, you know, we already had this, so maybe this is very easy to see. It's the same as, why don't we write this? It's the same as what? Okay, so we know we can write the probability of, we can say the probability of A and B is the same as the probability of what? B and A. So, should I do this now, or maybe it would be more helpful to do this later? Let me just look ahead for a minute. Let's just do that. I mean, this is just fine to look at it that way. Okay? I think I'll explain it later when we get to, yeah. All right. Now, so what are we going to do here? Okay, so sometimes it's just easier to do this intuitively and to use tables here. So these conditional probabilities, when there's just two events, are very easy to use a table, okay? So in the case where, let's look at this. Suppose a box contains 30 aspirins and 70 Tylenols. Half the aspirins and 10% of the Tylenols are poisoned. Fill in the table below. So let's fill in this table and let's look. So there's 100 total. And how many? 30 aspirins and 70 Tylenols. And what do we know? We know that half of these aspirins are poisoned. So half aren't. And what else do we know? That of the 70, 10% are poisoned. So that means 7 are poisoned and 63 are not. So now we can get these total number of poisoned here, which is 22, and the total number right here of not poisoned, and they should add up to 100. Okay, so these are useful when doing these conditional probabilities to make a table like this. So what's the probability of randomly drawing a pill from the box and getting a poison? So the probability of a poison is equal to what? The probability of a poison is, well, how many out of all of them, it's saying, how many? 22, okay? So the poison out of the total. 22 poison out of 100 total. Now, what's the probability of randomly drawing a pill from the box and getting a poisoned aspirin? Okay, so now that's the probability of poison and aspirin. So poison and aspirin. So still out of 100, so where's that? What's that? Out of 100, how many are both aspirin and poison? 15. Okay, now here's example of conditional probability here. If someone randomly draws an aspirin, there's a 50% chance that it's poison, right? If somebody randomly draws an aspirin, let's say, there's a 50-50 chance that it's poison. Does that mean that if someone randomly draws a poison pill, there's a 50-50 chance that it's aspirin? No. So this illustrates that A given B, the probability of A given B is not the same as the probability of B given A. So this is asking you, what's the probability that it's aspirin given that it's poison? So we want the probability of poison given that it's aspirin. So how would we do that? What you do is say, given that it's aspirin here, out of these 20, out of these 30 that it's aspirin, these 15, right? No, it says given that it's poison. I read that. This is wrong. My initial thing was right. I read it wrong. So we have to say, what's the probability that it's aspirin given that it's poison? And look what I just did. I did this wrong. I'm very sorry. And I didn't do it on purpose to hear those little, you guys are so great. You always do those little, oh, no. And that alerts me. I love it. What did I do wrong? Given that it's poison. Duh, Ellen. Okay, so given that it's poison, right? Poison. What's the probability that it's aspirin? Okay, given that it's poison. So I look for where? The poison. How many of those are aspirin? And that's what I want. Does everybody understand? And that's not the same as the other one. So the probability of A given B is not the same as B given A, is all I'm trying to point out. And sometimes making a mistake helps probably. Okay. So where was the other one? We should put it down. This was the probability of what? Somebody ran, there's a, okay. So this is the probability of poison. Let's write it down. Given aspirin. That. And that, given that it's an aspirin, there's 30, and that's the 50-50. So those two things are not the same. Okay. Now, so this is just some definitions, and contingency tables is called a contingency table right here. These numbers in these margins, right here, they're called marginal probabilities. And the ones inside here are joint probabilities because they're the probabilities that two things jointly happen, like aspirin and poison, or Tylenol and not poison, whereas these are just the marginal ones. Okay? So your answer to what? To which and above is a marginal probability. And your answer to what is a joint probability. Okay, so your answer to A, I should fill this in right here. Let's fill this in, which I'll say your answer to A is what? And your answer to, which one should I do for this one? B. Okay. Right? Isn't that right? Wait, your answer to A is a marginal probability, and your answer to B, anything inside here, is a joint probability. Okay? So that's a joint probability, and this 30 out of 100 or 22, any of these out of 100 is a marginal, and inside here out of 100 is a joint. Okay, because it gives the probability of being both a poison and an aspirin. All right, so part C, what was this? So what we did here with this one is an example showing that these two things are not the same, that the probability of A given B is not the same as the probability of B given A. And there's a lot of obvious examples of this, like the probability of being a man given that you're human is not the same as the probability of human given you're a man. I mean, it's pretty obvious, you know. Like that's, can you think of some obvious ones? Like, that's a good one. So the probability of being a man, given you're a human being, is not the same as the probability of being what? A human, given you're a man. That's kind of crazy because the probability is about 50%. And given you're a man, what's the probability of being human? Maybe about 95%. That's 100%. I'm making a joke there. So, because here's humans, and here's men. All right, so that's all you can see for sure. Now let's move on. I think this one's pretty much the same, but we can do it. Like, these tables are very useful. On the next page, we'll see how we can use Bayes' formula to do the same, but for simple cases like this, it's really not necessary. So, all right. So now we're looking here, and we're saying, suppose jurors make the right decision about guilt and innocence 95% of the time, and that 80% of all defendants are truly guilty. So let's say we have 100 defendants. 80 of them are truly guilty. That means 20 of them are innocent. All right, so in doing this, I would suggest you do this column first. Get the totals first. If you're going to do a problem like this. Okay. And then what are we going to do? Why don't we fill this table in, okay? So how are we going to fill this table in? We did the 80%. What about this 95%? Where does that go? What does it say? They're making the right decision 95% of the times. So this is to acquit them, and this is to convict them. So the right decision, if they're innocent, is to acquit them and let them go home, right? That's the right decision. So if they make the right decision when they're innocent, we'd want 95% of these 20, let's say they do. So for 19 out of the 20 people, they correctly were let go and didn't have to, just went right home. Now, if you're guilty, the right decision is to convict the person. And so 95%, let's say they make the right decision here, 95% of these 80 will be correctly convicted, which means 4 of them will walk free when they shouldn't. So now we can get the totals here. So this is 23, and this is 77. All right, so now what's the probability that a person is convicted? So you might think, what's the probability of a person being convicted if they're innocent? So this is a wrong decision, and you might think 5%, right? And that's what it is, right? If they're convicted, it's 1 out of 20, 5%. But now, what's the probability? That's what's given to you. The probability, that's what this 95% tells you. But now, what if we want to reverse these probabilities and figure out the probability of being innocent if convicted? Now, don't think that's necessarily the 5% again. It's a different question. So now you have to look at the people who are convicted, and out of the 77, only 1 is innocent. So that's not necessarily, it's less than 5% in this case. It would only be the same as if it was 50-50 here. Then this 95%, these could be reversed and they'd be the same. But it's not 50-50 here. Okay, so you'll see this with medical tests all the time, particularly with rare diseases, which is usually what they're testing for, like AIDS. So we look at this and it says, this is from real data, if a blood sample has the AIDS virus, then there's a 99% chance that ELISA will correctly give a positive result. This is a common test to detect AIDS in people's blood who are donating blood. So if the blood sample does not have AIDS, then there's still a 6% probability that AIDS will incorrectly give a positive result. Okay, so this is a false positive. And this is a true positive. Now, this is a rare disease, so only about 1 out of 100 people who've been tested of the blood samples really have the AIDS virus. So we'll fill in this column first. Out of 100 people, only 1 have it and 99 don't. But before we do this, let's use our intuition. So what do you think? Okay, so somebody, you see that this test is 99%, if you really have AIDS, there's a 99% probability that Alyssa will correctly give a positive result. And there's only this, and if you don't have AIDS, there's only a 6% false positive rate. So given those numbers, the question is here, what's the probability someone has the, well, first we can do this one. What's the probability someone tested positive given that the person has AIDS? Well, given that the person has AIDS, isn't that what this is saying? The probability of positive given AIDS. So it says right here that it will correctly, if the blood sample has AIDS, given that it has AIDS, then 99% of the time. So this is 99%. But what if, this is usually what we're interested in, is what if you get a positive result and the doctor calls you up and say, we got a positive result, which has happened to me, not with this, but with another medical test. That's why I'm very interested in this. I got called up and said, you've got a positive result and you better come in. And they mistook this probability. You know, you have a 99% chance of the disease or something close to that, when it really is something different. Okay, so what's the probability of having AIDS given you tested positive? And the way you can think of this is how I thought of it to calm myself down was I found out, you know, how many people had the disease. That's this. All right, and I said, okay, this is how I imagined it. Let's say it was with AIDS that they called me up about. So there's 100 people who have AIDS. So think about this, 100 people. Now, out of those 100 people, how many have AIDS? 1. This is exactly what I did because I was pretty worried about it. And then the other one is how many people don't? 99 people don't. Okay, this one person, I want to get this positive rate. I want to know how many people tested positive, basically. What's the probability of testing positive? Out of these 100, how many tested positive? So one person has AIDS. There's a 99% chance, so I just said in my head, okay, that's 1 true positive. That person really got, is that me? That person really got a positive. Or, out of all these almost 100 people who don't have AIDS, how many of them are also going to get a positive result? A false positive. How many false positives? So I thought, okay, so here's the 6 false positives. It's out of 99, but let's just round. So here we get, these people, we get 6 false positives. Now, I have this, the probability of positives. It's 7 out of 100, 7, so I'll put that in the denominator. Altogether, there are 7 positives. And I'm just, what's the chance that I really have it? So there's 1 true positive over 7 total. 1 and 6, 7 total positives. So that's the idea, and that's how you should think about it. This right here, you can only look at these numbers and do your intuition if these numbers are 50-50. same here, but they're usually not. And in a rare disease, which mostly is what you get tested for, so it was very, very comforting to me. It was for breast cancer, and I really got this result. They were going to schedule me for surgery and everything, and then I looked up the data, and I thought, oh boy, this is very helpful to try to understand this, especially if you're going into the, if you're a doctor yourself, going to become a doctor or in the health field, to understand these numbers, that these two things are not the same. So let's fill out the chart here with the, this is just the intuition, and let's just do what we know. All right, so this 99% says that if you have AIDS, 99% of the one, okay, so we have 0.99 there, and that means they have to add to 1 here, so that means that only 1% will get a negative. And this person well, let's just keep going. Now, the blood does not have AIDS, all right? Now, these are the false positive rates right here, that if the sample does not have AIDS, this is at 6%. So the 6% false positives are right here, 6% of 99. We called it 6, but it's actually a tiny bit less. So when we add those together, we don't get 7. We get very close to it, though. All right, that was our estimate of that number of total positives. And now we can figure out the rest of it here. So this is 93.06, and this is 93.07. Okay? Any questions on that? So that leads us to Bayes' rule, because that's another way to do this problem, and this is where it's usually used for us, problems like this. Okay, so Bayes' rule is a way to, this is Bayes' rule, and it's a way to reverse probabilities, finding the probability of A given B from B given A and vice versa. That's exactly what we've been doing with the contingency tables. All right, now, first of all, that's what I was going to tell you about over here, but I figured I'd wait till here. So let's just do that same thing. So we have some sample space here, probability of, okay, so we have this right here. Let's just remember this right here, probability of A times B. That's what? That's the probability of A and B. That's the rule for it. If they're independent, that A isn't there. If they're dependent, it is. So this is what we have. Bayes' rule says that A given B is the probability of A and B over the probability of B. And that's what we just did before. The picture was like you have A, and here B, and this right here is, so this is A, and this is B, and that's A plus B. So this makes sense. A given B is right here, A and B, right? That's A and B, that's what that is, the intersection, and then over B. So that's all probable. That's all it's telling you, what we already had before, right? It's the same rule. But if you, another way to think of it, it's really easy to think of it to get to this if you weren't sure, is thinking what? The probability of A and B is going to be equal to what? The probability of B and A, right? Those two things are the same, right? That's this intersection. A and B is the same as B and A. Now, and so what's probability of A and B? The probability of A and B is the probability of A. It's going to be hard to write over that. I'll just go down here. It's the probability of A, right, times the probability of B. But I have to make that little adjustment given what? If they're independent, that's right, but then given what? That A has happened, you can write it that way, or you could write it like this. Probability of B and A, you could say that's the probability of B, they're the same, times the probability of what? A, right? That's if they're independent, but if they're dependent, we just have to make sure we put that in. So that's what we have, and then if we divide both sides by the probability of B, then, you know, if you divide this side by the probability and this side by the probability of B, you get that. You get the probability of A, you get exactly that. Right? Does that make sense? So you can always do that. All right, now, All right, so let's do this. What did we do? Now that let's write our table here. So our table, let's just look over here. We might as well write this down. So this was 6.93, 93.07. This was 0.99, 5.94, 0.01, right, and 93.06. And this was 1 and 99. All right, now, let me see if I'll, okay. Okay, so what are we going to do here? So this is a probability right here of A and B right there, right? So what we ended up getting was, right here, we said, we never filled it in. I'm so sorry. So I'm going to go back and do it. We never filled this in right here. We should have filled this in, and we should have said what? That's the probability. It's here, 0.99 of the people who tested positive, right? How of the people right here who tested positive, that was 6.93, only one of them had AIDS. So that's our total, and how many really had AIDS. So this was what we got, and we could have also gotten this by Bayes' rule, okay? So let's just write down what we got. So this we got right here as 0.99 over 6.93. So what we're doing is we're doing this over that right here, because this probability of a positive, all the positives, was hard to get, right? We got, so how did we, so that's what this says. But what's, this is the probability, let's say probability of B is the probability of this positive test result. That's right down here. That's hard to get. We know this, the probability of A, right? We know that one, but we don't know this probability of B. Okay, so now, so we know the probability of AIDS given positive result. We know the probability of positive giving AIDS, that's 0.99, but we don't know this one. And so this was the one that's hard to get. And how do you get that? We couldn't get, so Bayes' rules usually that's not given, so this is what Bayes' rule usually looks like. And all it's doing is dividing up these two probabilities into two parts. This part, the probability of a positive when you have AIDS, that's the 0.99 right here. And the probability of positive when you don't have AIDS, right? B is the probability of a positive result. So that's the 5.94. And it's just adding those two together, right? So this is what they want to get here. This is the 6.93. I guess it's expressed as a fraction, so I should have out of 100, because these are out of 100. So out of 100, this right here is what that is. That's what that is. And these two, you can see where they match up. So it's just adding these two together. So we did it with a table, but this is Bayes' rule. It looks so complicated, but if you think of it, all it's trying to do is, when this is hard to get, it separates it into these two pieces, and that's all that's happening. Separates the probability of B into this, when A does happen and when A doesn't happen. That's all that is. All right. So, and so this right here works out to be 0.99 over 0.99 plus 5.94, except they divided the top and bottom here by 100, if you do it with these probabilities. All right. I mean, that's here, the top. These are divided by 100. Okay, so you're going to have to know this? No, but you'll see it. The reason why it's so important is because so many times that you can't write just a simple chart. And it's very important to understand that so you can do, you can apply that when it's more complicated. And Bayesian statistics, a whole branch of statistics, is based on Bayes' rule. And it's very, very useful. So I just want you to understand the basic rule and not find it mysterious. It makes sense. And then you can apply that rule when things get complicated. You could even derive it yourself. You just know it. You don't have to memorize it. At least I do because of thinking of it this way. Okay. Now, so you can do the problem with chart, but you don't need the formula. If you can do the problems with the chart, it's just helpful to do more complicated problems. Okay? All right. But for now, let's just move on because we only have 10 minutes left here. Okay, or 10, 15 minutes left. So now this is the addition rule. This is the probability that either A happens or B happens. Okay, so first let's just think about, so what is the addition rule? The addition rule is the probability, not that A and, but that either A or B happens. And we'll fill that in later after we think about it, okay? Let's just think about it first. Okay, so sometimes it's helpful to list all the ways that a probability process can turn out, okay? So this is a 6x6 little chart that lists all the different things that can happen when you roll 2 dice and take the sum of the 2 dice. So what's the probability of rolling 2 dice and getting a sum of 4? So sometimes the easiest way to think of it is the probability of getting a sum of 4 is just to count the probabilities, right? So how many ways can you get a 4? Well, you could get a 1 and a 3, a 3 and a 1. See, a sum of 4, these 3, right? You could get a 1 and a 3, adds up to 4. A 3 and a 1 adds up to 4. And a 2 and a 2 adds up to 4. So there's how many possibilities out of the 36? There's 3 ways. So now, what's the probability of rolling 2 dice and getting a sum of 7? How many ways are there to get 7? Let's see, 1 and 6, 6 and 1. What else is there? 2 and 5, 5 and 2, 3 and 4, 4 and 3. Is there anything else? Can you think of any others? No. So the probability of a sum of 7 out of the 36 is, and you can see 1, 2, 3, 4, 5, 6 ways. And how about 8? What's the probability of an 8? You can count them all up. The probability of an 8 is what? Getting an 8 would be, how many ways are there to get 8? Could you get a 2 and a 6 is 8. A 6 and a 2. How about a 1 and a 7? Does that work? How about a 3 and a 5 and a 5 and a 3? Does that work? Yes. Is there any other way to do it? A 4 and a 4. Should I write that twice? No, it's the same thing. You can see there's just one way to get 8 with 2 4s. There's 2 ways. You could have 3 and a 5 or 5 and 6. So it's 1, 2, 3, 4, 5. So there's just 5 out of 36. All right, so now let's just turn the page here. So now this multiplication rule that I was going to write at the top of the page before, but I'll write it here, is what? The probability of okay, so the addition, we've already done this one. This is our multiplication rule. Okay, so now we want this addition rule. So that's the probability of A or B. So if we drew the picture, it's not the intersection, it's the union. Here's A, and let's say we have a B. So it's going to be all of this. So we're going to add A plus B, but then we have this overlap here. So it's the probability of all of A plus the probability of all of B, but we don't want to double count this intersection here, the probability of both. You don't want that. But if they're mutually exclusive, that means that if A happens, mutually exclusive would look like this. Okay? Then you don't have, the union would be just this plus this. You don't have to subtract anything because you're not double counting anything. So that's mutually exclusive or disjoint. All right, if their intersection is 0. So now let's see, let's skip to an example here. We don't have much time, so let's just do some examples. So we'll skip that for now. And so here is the picture. This is when they are mutually exclusive. You can't be both A and B. And this is when they're not mutually exclusive. This is mutually exclusive or disjoint, and this is not mutually exclusive because you can be both. All right, so let's do some examples here. What's the probability of getting either a 5 or a 6 on one roll? On one roll, if you got a 5, so this is the probability of 5 or 6. So let's think of the rule. It's the probability of 5 plus the probability of 6 minus the probability of both. But they're mutually exclusive. It's one roll. So these are mutually exclusive. If you rolled a 5, it couldn't have been a 6. So this is just going to be just 1/6 plus 1/6. But, and this one is also mutually exclusive. You just draw one card. It's just going to be the probability of a heart or a spade is just going to be equal to the probability of a heart is 13 out of 52 plus the probability of half the cards. And one card can't be both. But now let's look at a case where both could happen. So if you don't want to double count if they both could happen, so here's an example. Getting either a heart or a queen. So the picture would be what? You have these 13 hearts here, and you have 4 queens, but one of them is both, the queen of hearts. But this is the queen of hearts. She's both a heart and a queen. This is a queen, 4 queens. Okay, so they're not mutually exclusive because you can be both. So the probability of a heart or a queen is going to be equal to what? There's 13 out of all the 52 cards, plus 4 out of the 52 cards, but then there's one of them that's both. So it's 16 out of the 52. That's your answer. So, oh, shoot, why didn't somebody say something? You couldn't see anything I was writing, right? What? Yeah. You're too dead at this point to bother? I didn't hear any. Did you say something and I didn't hear it? It's just obvious to you? Oh my gosh, you guys are too good this way. All right, so now what's the probability of rolling a die twice and getting either a 5 or a 6? Getting a 5 on the first roll and a 6 on the second. They're not mutually exclusive, no, because you could get, both could happen. So the probability of a 5 on the first, or, we want or, a 6 on the second is equal to what? That's the probability. It's going to be 1 out of 6 plus 1 out of 6 minus the probability of both. What's both? 1 out of 6 times 1 out of 6. So your answer is going to be what? It will be 11 out of 36. Because that's 12 out of 36, so it's 11 out of 36. The picture, see picture. Okay, so here, which ones, let's say this is the first. We can say call one the first and one the second. I don't care which one you call the first. We can call this the first and this is the second. It really doesn't matter. So getting, what did we say, a 5 on the first is this, 6 ways, right? And a 6 on the second is this. And so we double counted this. So we have 6 over 36, which is 1/6, plus 6 over 36 minus 1 out of 36. We double counted that one. All right. So now, what do we want to do the next one? Okay, what's the probability of getting at least 1? So at least 1 could be a 1, 2, 3, 4, 5, 6. Wow, that is a problem of using the addition rule, but it's much, much easier to do what we already know. So let's do that instead. So at least 1, do you remember the probability of at least? Much easier to figure out the complement. We have 6 rolls, and we want that, okay? It's much easier to find out 1 minus the probability of none. No 5s. So that's 1 minus probability of no 5s. No 5s on the first is 5 out of 6, and there's 6 rolls, so it's going to look like that. Not getting all 2s, okay? Probability of not all, again, that's really hard to figure out. On how many rolls? 3 rolls. Not all 2s. So 1, you either get not all, right, which means everything except 3, so 0, 1, and 2. So the probability of all 3s. That's 1 minus, what's the probability? 1/6, 3 rolls. Third. Okay, I think that's it. This one right here, see picture, page, just to remind you, because that one kind of is confusing to people. Let's see picture on page 40. Will help explain it. And then what did we skip here? So we skipped this. We can pick it up later on page 41. And the other page I said I would post. I think we did everything else. So we finished that, and okay, that's it for today.